Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about the Lebesgue integral in n dimensions. And indeed, in today's part 19, we will go back to the LP spaces and show that they are complete. So we have well-defined Banach spaces, and I can tell you that this result is often called the Riesz-Fischer theorem. However, as always, before we start writing down the proof of it, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And as you might know, as a Steady or Patreon member, you can download the additional material with the link in the description. And now, without further ado, let's recall the definition of the LP space on Rn. And usually there, P is chosen as a real number in the interval from 1 to infinity. And here we will not cover the case that P is equal to infinity, because we have already done that in the last video. Hence, in this video we can simply define the curved LP space as the set of measurable functions where the pth power is integrable. And then to get the straight LP space, we just have to go to equivalence classes. And there the equivalence relation is easy to define. We just say that f and g are equivalent if they coincide almost everywhere. And this simply means the set of points where they don't coincide has Lebesgue measure 0. And this whole thing makes it possible to define a proper norm on LP. This is the so-called LP norm, and if we want to be precise, we should write it down for an equivalence class in LP. However, the definition is quite simple. Just take a representative f and integrate the pth power of it. And then the result is taken to the power 1 over p. And now one can show that this one satisfies all the properties of a norm. So we have a nice normed vector space, and in today's video we will show that this one is actually a complete normed vector space. And some, but not all people, call this result the Riesz-Fischer theorem. So the formulation is quite simple. LP together with the P norm is complete. Or in other words, you could say this one is a Banach space. So this is already the whole statement, and what we will do now is to prove it. And as always, in order to get the completeness, we have to show that every Cauchy sequence in the space is actually a convergent sequence. Hence, the starting point here is simply to take a Cauchy sequence of equivalence classes in LP. And now we just have to construct another equivalence class in LP that is the limit of this Cauchy sequence. And now, in order to not have a conflict with the dimension n of our space here, we can call the index of the Cauchy sequence m. Moreover, this also tells you that we can go away from the equivalence classes and just look at the explicit functions fm. So it's not a big difference, just to note it, now we work in the curved LP. And obviously the property of the Cauchy sequence also holds for the representatives. This means if you look at the difference of two sequence members in the LP norm, then this one goes to 0. More precisely, this should happen when the two indices m and l go to infinity. So this also implies that we can choose two different indices and make this norm as small as we want. And now let's say for every integer k, we want to have it smaller than 1 over 2 to the power k. We want that because we know that the sum over these numbers is the geometric series, so it has a finite value. Therefore, what we do is to choose a subsequence which we call fmk. And then, as already mentioned, the difference between two sequence members should be less than 1 over 2 to the power k. So we have fmk plus 1 and fmk. And obviously the difference should be measured in the LP norm. And now please note, if we can show that this subsequence is convergent, then we also know that the original Cauchy sequence has to be convergent as well. This is just a standard property of a Cauchy sequence. And now in the next step, let's define some auxiliary functions that will help us in the proof. These functions should have non-negative values, and let's call them gk. And indeed, for every point x in Rn, I just want to sum up the differences we have for the functions fmk. So we have a finite sum that goes from 1 to k. And inside we just have the absolute value of the difference of fmj plus 1 and fmj. And we just use this difference at every point x in Rn. And this definition immediately implies that the pointwise limit of this sequence of functions definitely exists, but it could have the value infinity. So let's simply call this limit function g of x. So please don't forget, every positive real number here could be a value, but 0 and infinity are also possible. Of course, the best thing for us would be that the set of points where the value infinity is reached has Lebesgue measure 0. And in fact, this is something we will show soon. But first we will see that the functions gk lie in LP as well. This means the LP norm of gk is a finite number. And this is actually quite easy to show because we have the definition of the function. This just tells us that we have a whole sum of functions inside the LP norm. And then the standard triangle inequality allows us to pull the sum out. And moreover, then we also don't need to write the absolute value anymore because it's given in the definition of the P norm anyway. And now you can recognize that the definition of our subsequence comes in. So this norm here is less than 1 over 2 to the power j. And summing that up from 1 to k gives us, with the geometric sum formula, a number less than 1. And this is all we need, because it immediately tells us that the P norm of gk is finite for every k. And now you might have the following question: can this change for the pointwise limit, so for the function g? And in order to answer this, let's simply look at the integral over Rn of the function g to the power p. This integral is well defined because the worst thing that could happen to this is that it is equal to infinity. However, now we will show that this one is actually not the case. And the first thing we can do here is that instead of g, we use the sequence of function gk in the pointwise limit. And of course, if the limit exists, and we know that, then we can also use the limit inferior for it. This description is helpful because then we can just use Fatou's lemma from measure theory. This is a really nice result because it always holds when we have a sequence of measurable functions with values in this interval. And then we can always pull out the limit inferior and we get this inequality. So we don't have to check for anything else, and this is the reason I want to use it here. And then you should see that these integrals here on the right hand side are all bounded by 1. Therefore the bound also holds for our limit inferior. So the final result we have here is that the integral on the left has a finite value. And obviously this implies that g also lies in LP. And moreover, this one now also tells us that a set of points x where g of x is equal to infinity has to have Lebesgue measure 0. Otherwise, obviously, this integral here could not be finite. And with that, we are finally ready to define our limit function f. And first of all, we don't have to care about what happens at a set with Lebesgue measure 0, so there we will set it to 0. Again, this should be the case where g of x is equal to infinity. And now for the other points, I want to use our infinite sum, but without the absolute value. This means we take the difference here of the two neighbors and then we send k to infinity. And we know that this gives us a complex number that exists because we know we have the convergence with the absolute value. So this is just analysis knowledge. An absolutely convergent series is definitely also convergent. And now in addition, what I want to do is to put this first member here in the front, because then we have this nice telescoping property. In other words, this already leads us to the limit of fmj, where j is sent to infinity. In other words, in the second case here, f of x is exactly the pointwise limit of this sequence of functions. So this is already quite nice, but we also have to show the convergence with respect to the LP norm as well. But obviously, this will only help us if we also know that f is an LP. Indeed, both things go hand in hand, so let's start with the convergence. So first, please remember that we are working with a Cauchy sequence here, so for every epsilon greater than 0, we can find an index that we can call capital N, such that for larger indices that we can call j and k, we get that the difference between the two functions is less than epsilon measured with the LP norm. And this fact we now can use to estimate such a difference where the function f is involved. And as often when we want to go to the integral itself, it's better to look at the pth power of the whole norm. So then we have this nice integral here, and we already know that f of x can be substituted by the pointwise limit. And now as before, it's actually quite helpful to replace the limit by the limit inferior, because then we don't have to think much and can just apply Fatou's lemma again. This means we get an inequality where the limit inferior is now in front of the integral. And then you see what remains on the right hand side is almost our p norm again. More precisely, it's exactly the same thing we have written before, just to the pth power. Hence we know if the indices are greater than our capital N, then the whole thing is less than epsilon to the power p. And then we can immediately conclude that the p norm of fmj minus f is less than epsilon. And please note, this nice result holds for every j that is greater than the capital N. This means we definitely also get it when we send j to infinity. And then just to be careful, we should look at the limit superior, which definitely exists, and here we don't have a strict inequality anymore. However, since our epsilon was arbitrarily chosen at the beginning anyway, there's only one conclusion here. Namely, this limit superior has to vanish. And then obviously this also means that the limit itself exists as well. So in short, we have the convergence fmj to f with respect to the p norm. And this is the result that we wanted. The Cauchy sequence is convergent. However, this only works if the limit itself also lies in the corresponding space, which means f should be in LP as well. But the good thing is this is quite easy to show because we can artificially rewrite f as a linear combination in LP. So for example, let's use the fmj from before and let's subtract this difference. This clearly gives us our function f back, but now we can use the information we have for the difference. Namely, it has a finite p norm, which means it lies in LP as well. And on the other hand, the first part here also lies in LP. And now since LP is a vector space, a linear combination cannot leave it. And with that we have everything, and we can say that the Cauchy sequence is convergent in LP. And if you want, in the end here we can write it with the equivalence classes again. So this Cauchy sequence in the straight LP is convergent to the equivalence class of f. And please don't forget, the important part is that this convergence is with respect to the LP norm. And exactly this property makes the whole norm space complete. So there we have it. This is the whole proof of the Riesz-Fischer theorem. So I think this is good enough for today. Thank you for listening, and I wish you a nice day. Bye bye.